Welcome to lecture 34. In this lecture, I want to prepare the way for cosmology. Recall that we have the field equations of general relativity, which takes this form here. So on the left-hand side, we have geometric quantities such as the Ricci tensor, the Ricci scalar, the metric, the cosmological constant. And on the right-hand side, we have the matter part, which is expressed through the energy momentum tensor T mu. In most of the previous lectures, we have made simplifying assumptions in order to get solutions of the GR field equations. Mostly, these assumptions were that the solutions we were looking for were static or time independent and spherically symmetric, so to have no obvious dependence on angles. And they were derived for empty space, where the energy momentum tensor was 0. And we also set the cosmological constant to 0. So by making all these assumptions, we simplified the equations, which allowed us to come up with analytic equations, such as the Schwarzschild solution. In the present lecture, I want to now consider relaxing at least one of these assumptions, or some of these assumptions. In particular, I want to allow time-dependent solutions, which will be necessary if we want to talk about cosmology. For simplicity, I will still assume spherical symmetry, but no more time independence of the metric. In order to discuss this in full generality, it turns out that I will have to discuss an aside, which is I will have to discuss purely spatial properties of geometries that are maximally symmetric. So if you just consider three-dimensional space, so no time, in spherical coordinates, we can write down the metric. The metric in Euclidean coordinates is just given by dr squared, or the line element squared is given as dr squared plus r squared d omega squared. Now we can take this metric and plug it into the three-dimensional Einstein equations, rij minus 1/2 gij r plus lambda gij, where on the right-hand side is still 0, so no matter content. If you plug in this spherically symmetric, or the metric for Euclidean coordinates in Euclidean metric in spherical coordinates, we find that it is a solution of Einstein equations if the cosmological constant is exactly 0. Now we can ask ourselves, well, what about solutions that are spherically symmetric in three-dimensional space that have non-vanishing cosmological constant? In order to do this, we just take our line element that we had for Euclidean spherical coordinates, and we just modify it by sticking in an arbitrary function b of r instead of 1 into this metric here. If we do this and we plug this into the Einstein field equations in 3 dimensions, we can solve this using our computer program to evaluate all the Ricci tensors and Ricci scalars. We find that this metric here is a solution if the function b of r is given by 1/1 minus lambda r squared. As an aside, we find that for these solutions, the Ricci scalar is given as 6 times lambda. So if lambda is a constant, this curvature, the Ricci curvature, will be a constant. And this is one of the properties of these maximally symmetric spaces. So now that we have the solution, we can write it in a slightly more standard form. The way to do this is that we introduce a scaled radius r hat by sort of rescaling the radius as the normal radius as r hat over square root of these lambda. So if we do this, then we find that the line element is given as 1 over lambda, so a constant times the scaled line element, and the scaled line element takes the following form. It's dr squared times 1 minus kappa r squared plus r squared d omega squared, where this kappa here is basically just dividing lambda by the absolute value of lambda. So kappa takes the 3 possible values, minus 1, 0, and plus 1. These correspond to negative cosmological constant, 0 cosmological constant, and positive cosmological constant. So that's essentially just a sine function of the cosmological constant. It turns out that these values of kappa correspond to 3 different scenarios for maximally symmetric spaces. What are these 3 different scenarios? Well, one of them we already know, that is kappa is 0 or no cosmological constant. In this case, we just get back Euclidean space. Lambda is 0. R is 0 because R is 6 times lambda. So that means that the curvature is 0 or we get flat space. But we have 2 other solutions. One of them is kappa is 1. This is known as the zither space. In this case, the cosmological constant is positive because R is 6 times lambda. That also means that the curvature is positive. And we find that we have a geometry that's known as elliptic geometry or elliptic space. Finally, we have kappa is -1. This corresponds to anti-de Sitter space or ADS space, which you might have heard before. In this case, the cosmological constant is negative, and the Ricci curvature is also negative. So this is a space of constant negative curvature, which is known as hyperbolic geometry or hyperbolic space. What do these correspond to? Well, you can picture these 3 different scenarios by basically drawing a triangle in these geometries and looking at the sum of angles. In Euclidean space, where we have kappa is 0, if we draw a triangle with angles alpha, beta, and gamma, Euclidean geometry ensures that the sum of the angles of the triangle is exactly equal to 180 degrees. By contrast, let us investigate now what happens to such a triangle in elliptic space. You can picture elliptic space as basically being the surface of a sphere, which has then positive constant curvature. And if we look at the sum of angles of a triangle on a sphere and you add them up, you find that the sum of the angles in an elliptic geometry is always bigger than 180 degrees. Finally, let's look at hyperbolic space, where kappa is -1. In this case, we have a constant negative curvature, and the sum of the angles in the triangle in hyperbolic geometry happens to be always less than 180 degrees. So these are 3 possibilities for the triangle in 3 different geometries, and that in principle lets you also tell you in which geometry you are in. So now that we've discussed these maximally symmetric spaces, let's look again at our Einstein field equations. We want to make some simplifying assumptions in order to come up with solutions to the GR field equations. The assumptions we want to make is isotropy. This basically for us means we want to sort of assume spherical symmetry as before. And we also want to assume homogeneity, which means that we don't allow any non-trivial dependence on R. So something like the Schwarzschild solution, where we had an explicit solution on R, is no longer allowed. In order to come up with solutions, we still have to make an ansatz for our metric. And in the following, I want to just guide you to how to find such an ansatz that allows these assumptions, but nevertheless will allow us to treat cosmology as an analytic problem. To get started, recall that the line element for Minkowski's space-time using Euclidean space as a sort of basis, maximally symmetric space-time there has just the following form in spherical coordinates. It's the s squared is minus the t squared plus the r squared plus r squared d omega squared. However, we just learned that besides Euclidean space, there are other geometries that are possible. These correspond to 3 different choices for the parameter kappa. So if you want to generalize our ansatz to non-Euclidean spaces, then we can do this by, instead of writing the Euclidean space part of the line element and replacing it by the generalized solution that we found from the Einstein field equations with arbitrary cosmological constant. So we have this ansatz here, where kappa again is 0, -1, or +1, and I have added this potential sort of constant here, that was this 1 over square root of the cosmological constant that we had in the previous slides. So for constant A here, this is potentially a solution to the Einstein field equations, but it is a static solution. So there is no need for us to sort of make these assumptions. We can relax this assumption, and this is what we'll do in order to treat cosmology. So we want to be able to allow and study dynamics, so time dependence. So in order to do this, we will now allow A to be a function of time. So the ansatz we will consider is the following. We'll have a line element that is given as minus dt squared plus a time-dependent function A times the space part, which can be either Euclidean or elliptic or hyperbolic in geometry. Again, kappa here takes the 3 possible values, minus 1, 0, and 1, and we don't want to presuppose the correct value that we should take for doing cosmology. This ansatz is called Friedmann-Lemaitre-Robertson-Walker, or FLRW metric, because of the gentlemen that in various forms have come up with an ansatz like these in the past. The FLRW metric provides the basic study block for doing cosmology. Once we have this metric, we will find that we can use it to study dynamics of the cosmos. But to do so first, we have to sort of plug it into the Einstein equations and see what the dynamical equations, the so-called Friedmann equations are, which is the topic of the next lecture.